One of the steps that we'll use to graph a rational function, that means one that's got a fraction, will be to find the horizontal asymptote. Now, a horizontal asymptote is just a guideline to help us graph our picture. It's not going to show up in every rational function, only in some of them. Since it's a horizontal asymptote, the way we'll express the equation for it is y equals a number. Remember that horizontal lines are always y equals some number. The way that we'll find what our horizontal asymptote will be is to compare the degree on top with the degree on bottom. The degree of the numerator compared to the degree of the denominator. Remember that the word degree means the highest exponent that you see when you are in one variable. Now, the way that I'll represent a horizontal asymptote to help us draw our picture will represent it with a dotted line, much as I have for these two pictures. The horizontal asymptotes shown in red. Now, when you're making that comparison of the degree with the top and the degree of the bottom, there are three cases that could occur. The first thing that could happen, you might have the top degree less than the bottom degree. Anytime that the top degree is less than the bottom degree, our horizontal asymptote will be located at y equals 0. This is a fancy way of saying the x-axis. So now with each of the functions here, notice that the degree on top is less than the degree on bottom. For this one, a constant value has a degree of 0, so our top degree is 0. On the bottom, the understood exponent that we have is a 1, so our bottom degree is just 1. Since the top is less than the bottom, then y equals 0 will be our horizontal asymptote. You can see from the picture that we've drawn that it's getting very, very close to the x-axis, but it's not going to touch it. It is possible sometimes to touch a horizontal asymptote, but it's very rare. It has to be a pretty fancy graph for us to touch the horizontal asymptote, and when we do, it happens in close to 0, 0. So for this particular picture, we're getting very close to the x-axis, but we're not going to be able to touch it. For the other function, notice that the degree on top was 1 and that the degree on the bottom is 2. So again, the top degree is less than the bottom. Anytime that your top degree is less than the bottom, the horizontal asymptote is going to be at y equals 0. The second case occurs when the degree on top is the same as the degree on bottom. If the degree on top is equal to the degree on bottom, our horizontal asymptote will be at y equals the ratio of leading coefficients. The ratio of the leading coefficients just means we'll take the leading coefficient on top and divide by the leading coefficient on bottom. So when we've got the top degree equal to the bottom degree, it's y equals the ratio of leading coefficients for our horizontal asymptote. For instance, on this first one, the degree on top is 1. The degree on bottom is also 1. Since the degrees are the same, the ratio of our leading coefficients will be where our horizontal asymptote is. Now, if you want to draw a picture of it, 3 over 2, 3 halves is 1 1/2. So through 1 1/2, we'll have a dotted line that we will approach with our picture, but we won't be crossing over it. One trick that you have to be aware of with horizontal asymptotes is if the terms are not written in descending order of power. Your leading coefficient comes from where you got your degree. Whichever term where you have gotten your degree, that is your leading coefficient. For instance, on this one, I have a degree of 1 on top and a degree of 1 on bottom. Our leading coefficients are from the top, -5, and from the bottom, 2. So my horizontal asymptote for that one is at -5/2. One more. For the one that is here, both parts have a degree of 1. That means y equals the ratio of leading coefficients. When there's not a coefficient listed, remember that it's understood to be 1. So for each part here, our leading coefficient was 1. That means our horizontal asymptote will be located at 1/1, which is just y equals 1. If the degrees on top and bottom are the same as each other, your horizontal asymptote occurs at y equals the ratio of leading coefficients. Each of our examples here had a degree of 1 for both top and bottom, but it could be any degree. If the degree on top matches the degree on bottom, ratio of leading coefficients will be your horizontal. The third case that can occur is if the top degree is more than the bottom. When the top degree is more than the bottom, there is no horizontal asymptote. The top degree more than the bottom eliminates horizontal asymptotes. If the top degree is exactly 1 more than the bottom, you can instead get what's called a slant or oblique asymptote. The top degree must be exactly 1 more than the bottom for a slant or oblique asymptote to occur. And remember, horizontal asymptotes and oblique asymptotes cannot be in the same problem. Let's look at some examples of case number 3, where the top is exactly 1 more than the bottom. This will give us a slant or oblique asymptote. To find the equation of the asymptote, all I want to do is to divide. Remember that what a fraction means is that we're dividing the top by the bottom. When I do this division, we'll throw away whatever remainder we have, and the equation of the slant asymptote will be y equals whatever our quotient was. Let's look at the example. For this one, notice that the top degree, 2, is exactly 1 more than the bottom degree, which was 1. Now, the official way for us to do this is with long division. So here I've set up long division. Whatever's on the bottom, that's our divisor on the outside of the box. Whatever is on top goes inside our box. Now x goes into x squared how many times? If I divide x squared by x, it will go x times. Once I've got something up here on top, I'll multiply it with whatever we were dividing by. X times x makes x squared. Just like with dividing in arithmetic, once we've done that multiplication, now I will subtract what we had as our product there. Now if I subtract, these x squares go away if I've done it right. For this particular problem, let's bring down 2x minus 1. As long as the degree here is the same or more than the degree there, I can continue to divide. So x goes into 2x 2 times. Let's multiply. 2 times x makes 2x. And again, let's subtract. The 2 x's have gone away, and we're left with a -1 remainder. Remember, we're going to throw the remainder away, so it doesn't matter. The equation for our oblique asymptote is y equals whatever quotient that you had. So for this one, y equals x plus 2 would be the equation for our oblique asymptote. Now I know that you probably are more comfortable doing synthetic division rather than long division. As long as you have a linear divisor, this means that it's got a degree of 1, then it's okay for you to use synthetic division. Remember again, degree on top, exactly one more than degree on bottom, so this one has an oblique asymptote. I've set up my synthetic division, coefficients on the inside. Remember that signs are part of coefficients, and also remember that if you have any missing terms, you'll have to have 0 as a placeholder. We're not missing any terms, so we don't need any zeros. On the outside, the thing I'm dividing by is our divisor set equal to 0 and solved. If you took x minus 1, set it equal to 0 and solved, you would get 1. This is what I'll divide by. Bring down our first number. Now multiply diagonally. 1 times 1 makes 1. Vertically I add -4. -4 times 1 is -4. Vertically we add, and the last spot is our remainder. We don't care about the remainder. All we care about is the quotient. The equation for our slant or oblique asymptote is just what the quotient says. If I started with an x squared, I've pulled one factor out, then our quotient says 1x minus 4. So the equation for our oblique asymptote is y equals x minus 4. For you to have an oblique or slant asymptote, the degree on top must be exactly one more than what's on bottom. When it is, do division to determine what the equation will be. Throw out the remainder, and y equals the quotient is the oblique asymptote's equation. There can never be an oblique asymptote and a horizontal asymptote in the same problem. They do not go together.